Okay, let's get started. Any questions from previous discussion? Yes.
이번 시간에 W가 P랑 렌즈 트랜스포메이션의 인디펜던트한 확률이라고 말씀해 주셨던.
No, it depends on P only in a sense that whether P is massive or massless. Right? So if it's massive, it is SU2, if it's massless, it is U1. Modules of some that level. So it depends on that level, but not every single P depends.
네, 끝나고 네.
Okay. All right. So let's continue. So last time, so here is a quick summary, but also nice eraser. Is this ours or no?
Yes.
Oh, okay. I figured. Very good. So let's recap briefly what we talked about last time. So we discussed how to construct a quantum field, which so far, we constructed a scalar field operator, right? But in particular, we put a special emphasis on, we introduce scalar field here, the field, as a formal machinery to implement the notion of Lorentz invariance, but on top of that, causality, right? And then how imposing those conditions restrict possible form of quantum field operator, right? So here is the condition we impose. First, let me just talk about one species for now. So one, we wanted to construct a field operator such that it vanishes outside of Lycom, so causality. And two, we focus ourselves on a real scalar field or Hermitian, so that this is directly related to observables in quantum physics. Okay, three, and then we imposed two Lorentz conditions. I don't know which one I wrote down first, but anyway, I'm just gonna write. I don't know which one I wrote first. Tell me. Just thinking whether it should be flipped. Oh, probably I wrote A here. And then X say. And then U dagger lambda. U lambda. And then since I'm talking about Lorentz, and then the last condition we imposed was this is linear in creation analogy operators, right? So and then we walk through the exercise. So by starting from step number one, what we tried was, okay, how about I start out with this ansatz with the Lorentz invariant measure, and then some function, as I demand is linear. And then condition number 4 says that it should be a constant function, literally basically constant. And then condition 2 impose that we're not talking about two separate, but basically they are complex conjugate of each other. Reality. And then from condition 3, translation and invariance. So we obtain the expression for field at arbitrary space and point. Now there's this. Minus P. And then F star. Okay. And then demanding. So here I already used the condition 5, right? Demanding causality, we found out that first of all, there can exist only one phi field for each particle species, right? So that's what we did exercise. So you may remember that the last exercise we did was that what if I have like F1 and F2, two different kind, and demanding that, basically what we found was, let me just remind you, so we did exercise with a potentially two different quantum field, and then we found out basically the following answer. So I, J star plus X minus Y, and then Fj, Y star, plus Y minus X. That's what we found, right? Good. So now we use the fact that if X minus Y is in such a way that is a space-like separated, meaning this, I argue that this should be equal to basically delta plus of X minus Y, right? Because you can always make a Lorentz transformation. So therefore, that condition reduced down to X minus Y, and then I probably put some non-mass information. And this is non-zero outside of Lycon, as we talked about, and then we are left with these two terms. Minus complex conjugate. So this is basically 2i times the imaginary part of Fi. So therefore, causality requires this is a non-zero function, this has to be zero, but that's only possible if this is real. That's only possible if they are the same thing and there's complex conjugate of each other, which is real, right? So that's what we talked about. Now, good. And then I say something about in this expression, instead of writing this, I basically wrote this way to emphasize that there's a certain cancellation between the two terms, right? And for this discussion, it wasn't particularly manifest or clear what that minus sign cancellation really means. Okay, so to really illustrate this point, and therefore, to be able to see the notion of antiparticle by eye, let us consider following exercise. Basically, we're going to walk through this exercise. Let's consider now, in order to illustrate, now I want to consider, now this is a complex field. Complex field. What it means is that the phi dagger is not equal to phi. Okay? Now, one way to approach this discussion is to consider two real scalar, phi 1, phi 2. So these are two real scalar. Okay? Then I can construct this as 1, 2, divided by square root of 2. Okay? Just to normalize. So then you see that this thing will look like, well, since I know the construction of the real scalar field, this will look like basically alpha 1, let me drop the key, plus alpha 2, so square root of 2, e to the I dot x. And then crucially here you will get 1 dagger, I, 2 dagger, again square root of 2, e to the plus I p x. Okay? Now, one important thing about this expression is the following thing. So let me call this entire expression to be my just alpha, okay? Okay? And then let me denote this everything to be just beta, dagger, okay? And I'm using a different notation because they're different. So you note that alpha dagger is not equal to beta dagger. That expression, right? Because alpha dagger, you should get alpha 1 minus 2 dagger over square root 2 instead of the plus. So that's not the same thing. Okay? In fact, using the fact that each of the alpha 1, alpha 2 satisfies require the computational relations. Okay, also for the two separately, but demanding that 1 and 2 commutes, including alpha dagger, meaning you start out with the two completely uncorrelated real scalars, right? and then you're putting them together. You can show that in that way that alpha and also beta that I wrote there in dropping P indeed satisfies required commutation relation. Okay. So now you have the two different objects, although there's some subtlety that I'm sort of glancing over at this point. I will clarify that later after I finish my exercise. Okay, so let's play with that complex scalar field, and we're gonna basically walk through very similar exercise. Good. So then we are about to now check the causality of this thing. But before that, let us ask what this field actually do. Right? What does this quantum field do? So first of all, note that if I had a phi, and imagine that I do sort of a U1 rotation, alpha, phi. Suppose I'm just gonna rotate that by this U1 phase. Then clearly, the dagger part will rotate with opposite phase. Okay? Now, you will learn much more about this type of operation soon. So this is the example of a symmetry transformation. We will spend a lot of time talking about it eventually. So for now, let me just tell you the answer, and then we're gonna again study that carefully. So this can be viewed as the fact that if you had a theory eventually, where theory respected these types of transformation, meaning the theory is invariant under that kind of rotation, then you can say that this quantum field, the phi, had a charge, say, 1. Like the electron has electric charge -1. Okay? Because I put 1 here. But in principle, you can put some charge Q there. Nobody stops that. And again, here. So then if a phi has a charge Q, phi dagger has charge, for instance, Q minus Q. Right? So phi dagger seems to have a different charge, opposite charge, for instance. Okay, but the second thing, which will make much more, physical, discussion being much more physical, let me ask the following questions. This is my time flow. Okay? You can just draw a straight line if you want. Okay, any other distance. Here's my time flow. And then let's pick a specific time flux. Okay? So this is a spatial slice, space-like slice. Okay? And then the way quantum mechanics works, obviously, is that here we're going to construct a Hilbert space at time t. And then, you can construct another time. You can construct the Hilbert space later. And then there is a time evolution that connects the two different Hilbert spaces. Okay? That's how things work. Now let's ask what this field does, right? Actually. And for that matter, now I can ask the following question. So here you have an alpha dagger and a beta dagger. And if you remember our discussion about many-body Fock space, then now you have two different kind of creation operators and associated annihilation operators. And you can imagine that this alpha dagger will create one kind of particle, and beta dagger will create another kind of particle. So in this theory, one particle Hilbert space will be factorized into, momentum P. So I really mean 3 momenta because I'm imposing one shell. But alpha kind of particle, which probably, for instance, as I explained, that will carry charge minus Q. And then you have this. So this is completeness relation. But this sector, this theory described by this quantum field has not only alpha particle sector, but it also has a beta particle which will carry plus charge. I say, how do I know? Beta carries plus charge or minus charge, which I will explain now. So therefore, the kind of question, in order to understand this Hilbert space structure, you can ask the following question. So let's take a vacuum, okay? No particle excitation at all. And then let me ask, okay, can I act with this quantum field, so there's time evolution, and then at some particular t, I'm going to act with my quantum field on the vacuum. And then I ask, does that have a non-trivial overlap with a momentum p alpha particle or not? Right? I can ask that question. Now, and then I can also ask whether that thing has a overlap with the beta particle set, right? I can ask that question. Is the physics question clear? There's time evolution, and then there's a vacuum. I'm going to act with my quantum field, which has both alpha beta, and then I ask which particle gets created by this particular operator. And then you sort of know the answer. I mean, you can do the explicit calculation. Phi is like alpha plus beta delta, structurally. So therefore, obviously, out of the vacuum, what you can create is a beta particle, right? Not the alpha particle, really. So you know that, therefore, I mean, you can carry an explicit calculation. You have explicit expression for the quantum field, write it down, and actually do the thing. But you see that certainly this cannot create an alpha particle, but it will create a beta particle. And then I told you that if I say that phi carries charge q, whatever particle created by the phi should carry charge q. Is that clear? And then if you actually do the explicit computation, you're going to get the things, basically. Like that. And then you can ask the same question. Exact same question. So now, let's do this following question. So momentum p alpha minus q state, but now I'm going to use instead phi dagger operator acting on the deck. And then I'm going to ask the same question. And again, the answer should be intuitively clear, because if you take a Hermitian conjugate of that, this will be now beta plus alpha dagger, right? So phi dagger is capable of creating alpha particle, but it cannot create a beta particle. So therefore, this should be 0. And then since it is created by the phi dagger, and the phi dagger, say, for instance, in this convention carries charge minus q. So such a particle should carry charge minus q. And then again, if you do the computation, you get the things like this. So what are we saying? What I'm saying is the following. Now, if we want to talk about the complex scalar field rather than the real Hermitian scalar field, now physically it is capable of dealing with two different kinds of species. Phi itself, out of the vacuum, can create a beta particle, and the phi dagger will create a particle, in this case now, alpha particle rather than the beta particle, right? It can create two different particles, but done by different operator. One is phi, the other is phi dagger. And crucially, there's an extra label that I had to introduce, right? Compared to the real scalar case, I had to talk about certain quantum number, in this case, charge I introduced. Okay, it can get much more complicated, but I'm taking the simplest case. Okay, so that's so far the picture. Therefore, one particle Hilbert space, one particle state Hilbert space consists of alpha and beta with opposite charge. So far, that's what I'm saying so far. Okay, now I'm going to ask a question of causality for this thing. Okay, so now let's ask the question of causality. So to ask the question, it is convenient to write as follows. So remember, this is like alpha plus beta dagger, right? So therefore, I'm going to write it as, so you know what I mean by that, right? I don't mean literally this. You know what I mean, right? You're not going to assume me. I have Professor out there, he can just write it. No, you know what I'm saying, right? Answer me. Yes. Okay. All right, so I'm going to basically decompose this thing with a plus. Remember, it is maximally confusing that, plus assigned to the minus with no dagger, right? Absolutely confusing notation. It was a historical disaster. I will spend some time today, hopefully if I have time, hopefully rectify that. Okay, and then, okay, so here I'm going to write it as this, and then there's that, okay? So that makes sense. Do you? Okay? And then since we have to talk about phi dagger operator, this is beta plus alpha dagger, right? And so I'm going to, you know what I mean. Now see who's with me. So let's check next Monday if how many of you survive. So are you with me so far? Okay. Are you? Okay, very good. So I'm kind enough. So this is alpha, right? This is alpha, this is beta dagger. Well, what am I doing? I really, but you know, I'm maximally kind, so I'm just going to too. Okay? We are ready. So the first causality check, which is phi and phi, automatically 0, because you always contract with alpha with alpha or alpha with a beta phi. But they are manifestly 0, right? Alpha commutator is 0, alpha dagger either, alpha beta is also 0. Where is it? Oh, I never read it down. Here we go. Alpha either with or without a dagger. Okay? If you do that, you can check explicitly. I already give you expression in terms of, let me just write it down. So alpha was, in terms of that construction was this. Beta or beta dagger, let me do it right. Beta dagger was alpha dagger 1 plus alpha dagger 2. So here's 1 non-zero, here's another non-zero, 2 i's minus sign, they cancel out, right? This is 0. So that's manifestly 0, because your only option is alpha with alpha or beta dagger with beta dagger. That's 0. And you can also quickly convince yourself that dagger part also vanishes outside of light. So the only non-trivial check that you can do is phi with a phi dagger, which I will do. Okay. Okay, so now let's do the last check. This is all. Let's check this. So I'm about to look at the commutator between these two. So basically, I need to look at that and that, right? Because that's the only non-trivial thing. Let me write it down. And this will have a non-trivial contribution from x dag plus alpha. My God. Minus. So alpha dagger, right? All right. Minus plus. That's beta dagger beta. Are you with me? And last time, when you look at things like this, right? We learned that that is what we invented to call delta plus of x minus y. But let's be careful though. Here, this is for alpha particle, correct? This is for the alpha particle. Let me just write the message explicitly down. Okay, there's some subtlety that I'm hiding under the log, in case you spot. If not, you're never gonna hear about that. Okay, that. So here, I can just switch this thing by taking a minus sign. And then now this is for beta particle, the same structure. So that's delta plus y minus x, but this is for the beta particle. Okay? Now, this, in case you've forgotten, this function looks like Lorentz invariant measure e to the probably minus that. So this is Lorentz invariant measure, Lorentz invariant function. So this is Lorentz invariant function overall, right? And so this should be equal to x minus y beta on space-like separation. You probably remember this picture that I showed you, right? Okay, so then how are we going to get the causality right? But this equation hopefully tell you more and clearer information about how causality works. In order for the causality to work, you need the following. For each alpha particle, you must have a beta particle such that one, mass has to be the same. B, charge of alpha, charge of beta, they have to be minus sign, right? opposite charge. So whenever you want to look at the space-like propagation, right? So the point here is that Tx, and then whenever you start asking this type of question, x, y, space-like separated, then the way quantum field theory works is that you will have a propagation by alpha particle, but at the same time, you must have a propagation by the beta particle who has the same mass, opposite charge, such that they exactly cancel. Okay? And that was the point I wanted to deliver last time, but it was sort of obscured when I was dealing with a single real scalar field. Because there, if you recall, instead of you see this particular structure, just saw Fi, Fj star minus complex conjugate times delta. So you couldn't quite say exactly that this actually meaning that there's a particle, antiparticle, which is the same same as itself. Okay, for real scalar, particle, antiparticle, literally the same, because the real means that it doesn't carry any charge. So mass is the same. Since it doesn't carry any charge, you could not quite spot that they are actually different particles. That's why it was a degenerate last time. Okay, but here complex scalar sort of reveals that they are actually different particle, but the causality works by having an exact cancellation. Whenever you look at the space-like separation propagation. But if I start looking at a time-like propagation, remember that for time-like propagation, you cannot flip this function with the opposite argument. Right? You cannot send this to here. Right? Only for the space-like separation, you can always send back. That's why you can have the exact cancellation. Okay? Good. Now, about the history. I'm going to spend just 5 minutes to clarify one point, okay? So, yes.
I can see the point 1, the mass, because it is encoded in the EP, right?
Yeah.
But I can see the necessity of
For this particular exercise or in general?
for this particular exercise.
For this particular exercise, the way it came from was that while this is produced by phi generator, a phi field, this was from the phi diagram.
But there is a secondary point. Right.
What do you mean secondary?
At the first point, at the first place, you didn't have to introduce the charge.
But then, again, particle and antiparticle are the same.
Why?
It doesn't carry. When you say, if you don't introduce charge, that means that somehow you're dealing with a quantum field which cannot be charged, right?
Yeah.
Which means it's a real field. Which means that there's no name tag that distinguishes particle from antiparticle.
But mass is different.
Are you talking about?
We can differently label the particle and particle by mass.
Sure, but then we're not gonna guarantee the causality. So okay, so I will make a one hormone problem. Basically, it's doing the same steps of calculation, but I will let you deal with some of. I'll give you basically alpha plus, and then beta. In the hormone problem, I'll give you basically separately. I'm not gonna even construct out of the two scalar field. I'm just gonna literally give you this building block. Okay? And then I let you combine, but then the only condition I demand is that you want to construct a single object. So you want to construct a single quantum field, at least as a linear combination of alpha or alpha dagger, or beta or beta dagger. So you have several combinations to work out. And a priori, you're going to combine these two with possibly different mass and different charges, right?
So the introduction of the charge in the story of the time is two different model. The
antiparticles?
It's a necessary in the following sense. Whenever you are asked to construct a quantum field with two different creation annihilation operators, by definition, this is not real. This is not permission, as I showed, right? That means that that field had to carry some charge. Meaning, it is not real, right? The associated particle can potentially carry charge, non-trivial charge. Or more precisely, it is impossible that they have the same charge.
혹시 이렇게 이해해야 돼요? 결국에 만약에 차질을 인트로덕션 하지 않고 이 스토리를 계속 진행했다고 하면
Which I did.
그러면 M 알파랑 M 베타 같다는 결론이 나와요.
Yes.
그럼 원파티클 스테이트는 결국에 모노토피랑 N으로만 라벨이 됐다면 결국에 그 알파 파티클이랑 베타 파티클은 결국에 원파티클 스테이트가 P랑 M 같은 N으로 지금 라벨이 됐다는 건데 그거는 저번 시간에 했던 그 유니클래스 때문에 같은 필드로 결국에 비교를 낼 수밖에 없다.
Yes, so the whole point is that I want to construct a single quantum field by housing several components together. But if you want to do it without necessarily including charge, then you're going to combine these two, possibly assuming that this may carry different charges, different masses. If you run, then if you run the same argument, then at least you have to conclude this. But I'm just telling you a more general story because your story is basically saying that this is zero.
테크니컬리는 그 사진은 결국에 파티클 라벨을 위해서 도입한 저번에 그 그냥 스킨처럼
Yes.
마치 스킨처럼 도입한 그런 걸로 이해하는 거죠.
Yes. Not really exact what level you are there, but whenever I combine two different particles, well, when I say already, I meant that, so by which I mean, they, okay, that's what I mean. Whenever I construct a quantum field with two sets of creation annihilation operator, by definition, such a quantum field cannot be real. Simply because it is not real, right? Hence, in principle, at least I can talk about the U1 charge, which I did. And if I imagine that theory respects such a charge, which is a dynamical question, this may have a non-equivalent charge, I don't know yet. But at least in the event that theory respects a certain charge, I'm saying that the causality tells me that not only the mass has to be the same, but charge has to satisfy precise condition. So we learn extra information.
저한테 느껴진 너무 시간 끌었거든요. 저한테 제가 느끼는 바로는 그 스토리를 진행하려면 반드시 저 띠어리가 유언 시민들을 가지고 있다는
No, I'm not even making that. Again, only with that, this is not real. So far you agree. There's no any dynamic information that I need to say that. And then what I said was, then this can potentially carry charge, minimally U1 charge. And if the theory respects that, then two particles have to satisfy this relationship. That's it. But maybe the dynamics actually break associated U1 charge, then you don't have to talk about this charge.
사진을 그 시메트리랑 연관된 녀석으로 보지 않고 그냥 원파티클 스펙트를 정의할 때 라벨을 다르게 한다는
Which is the same thing. I don't know what's the difference between those two. Level means quantum number, quantum means there's a symmetry. Right? Label is necessarily tied to the symmetry.
그러니까 레이블을 같게 하면은 M이 같다는 게 결국에 파티클, 알파 파티클이랑 베타 파티클의 그 스테이트가 정확하게 같은 레이블을 가지기 때문에 어제 월요일에 했던 그 유니클래스 티어리였잖아요. 그거에 의해서 두 필드는 같다라는 결론이 나오는 거죠. 따라서 레이블을 할 어떤 인덱스가 필요하고 그 말은 뭔 말이냐면 퍼터 스테이트의 레이블이 이 티어리는 뜻이 어떻게 그렇게 이런 식의
Yeah, I think you can walk through that logic too. Yes. So if I assume no extra thing, then I prove there's uniqueness theorem. Right? If the thing allows extra labeling or extra quantum number, which is typical for complex field as opposed to real field, then you have extra labeling, then you have this story that I always do. Okay. Good. Any other questions? Okay, so I'm gonna first move on, skipping the history for a second. And I will tell you the main story, and then I'll come back to this, because this is a side story. Or I can make one more. Okay, so good. Now, hopefully you appreciated the construction we have gone through, right? So we just combine the building blocks of quantum mechanics plus special relativity one by one, and we arrived at the fact that there is a notion of quantum field. In this case, we introduced this. This is at least a useful form of machinery, okay, of object, which can easily implement the notion of causality, unitarity, and concurrent invariance, right? So that was useful. Now, what I'm going to spend some time to discuss is that we can reverse the argument. So instead, so this is all good. Instead, from now on, we're going to take this quantum field as a fundamental object. Okay? Now you appreciate that this is useful here in this one way of arguing. Now we're gonna take a different approach. Let's just take this as a fundamental object. Okay? So we have to talk about quantum field to talk about relativistic particle and their interactions. Then you can ask, what conditions or properties have to be imposed on this quantum field such that, the physics or dynamics respects concurrent invariance, quantum mechanical unitarity, and lastly, virtually causality. Okay? So, again, let me make sure that you're on the same page. So, I constructed it, but let's forget about that for a second. Now, let's just ask. Let's take a quantum field is a fundamental object that I just want to use or play with it. And then I want to generate the set of physics out of that, okay, as you will learn how. But then can I let's ask, in order not to violate any of these kosher principles, what structural condition do you have to impose on this field? And then you can sort of not worry too much about very subtle tight balance between the special relativity and quantum mechanics, but just think about the conditions on the quantum field and just keep using it to generate the consistent physics. Okay, so that's sort of the thing that I want to spend some time on. So now let's recall the following thing to initiate the discussion. Let's recall that there's a T state that if we take the quantum field acting on the vacuum, then we saw that this is this, right? It gives you a fix. So there's a several way of looking at this expression. One way is straightforward way, which is to say that I already knew the form of quantum field. Do actual computation just to derive it. That's one way, right? To do that, you sort of have to know the answer already. Second way of looking at that is that you can probably remember whenever I write this notation, I actually mean that this is a state with a four momenta with the initial condition imposed. That's what I actually meant, right? So 4 variable with one constraint, therefore we need 3 independent. So we're going to just use these 3 independent. That's what we talked about. Again, now this is a wave function on the other hand, right? So this is a wave function. So there's a quantum state, you project it onto the momentum space. That's what you have done. Now you can ask, okay, so this, on the other hand, has to respect the Lorentz invariance. So there's a function, this is labeled by p mu, this is labeled by x mu. what could possibly be Lorentz invariant function made out of that? So you see, therefore, that it should be some function of p dot x. And then, physicality suggests that this basically describes a propagation of free particle. And free particle, if you think about it, can be described as a plane wave. And so what will be Lorentz invariant function describing plane wave, which is normalization, is this. So that's one way of arguing without actually using the answer array. Okay? Now, this, however, as we already stated here, you can say, okay, P in this expression, obviously, cannot be anything but P mu appearing in e to the x has to be what? It has to satisfy correct relativistic dispersibility, right? You can ask, how can you ensure that this condition will be fulfilled if you construct state out of this quantum field? And so this can be fulfilled if quantum operator satisfy in the momentum space sense this condition. I mean, it's a triviality statement almost. But if you pass on to the Poisson space, what that means is that you know that your quantum field has to satisfy this. So probably some of you have seen the derivation of a Klein-Gordon equation, starting from Lagrangian equations of motion and so on. That's already free-streamed, later version of quantum field theory. But here, without even talking anything about the Lagrangian yet, which we will next week, we already know that that thing had to satisfy that. So in that sense, we will introduce Lagrangian as another fancy machinery which guarantee you to get this equation that you already know that you have to get. Okay? Good. So we learned one thing. Now, so that's, let's say, this is the first step for that argument. Okay, yes.
But isn't this like looking for a problem that satisfies our solution?
Can you say that again?
Isn't it like looking for a problem that satisfies our solution? Which is
which one you view as a solution, which one you view as a problem?
So, I mean, like looking for a Lagrangian that would satisfy our solution once we go through the promotion.
That's actually rationale behind the Lagrangian. Historically, logically, most of the quantum field theory class, you start up, here's the Lagrangian, right? So here's my Lagrangian, don't worry about it, I'm gonna erase it very soon. Oh, whoa. And then professor told me that okay, this clearly described a scalar particle with a mass m propagating. And I was like, I don't see that at all. Where are they coming from? That looks like a random smoosh expression to me. Where they come from? Right? And that professor didn't answer my question because he said that. I was like, okay, I believe you. I don't know where they come from. But logical build-up towards this point is what I was trying to say. We know this had to be the right thing, but there is a condition, precondition, okay, which I will clarify momentarily. This is true description for free particle. Therefore, that will be deeply related to the fact that this is a linear in alpha diagram, not like polynomials. And then, as you said correctly, if you actually read Weinberg QFT, chapter 6 and 7, that's exactly he introduced the Lagrangian. Lagrangian, now I'm going to introduce you because I know you are lazy. I know you don't want to think through carefully. Forget it if you don't want. Just take this as initial point. This will produce all the results. It's guaranteed to be consistent with the causality unitary Poincare invariance. So this is a formal machinery introduced later. That now I want to forget about all these constructions. I just want to go no-brainer derivation. And then it gives you impression that you can actually understand things when you actually don't, without going through this exercise. Okay, so that's actually the rationale that we are taking here. Did I answer your question? As I promised, I'm going to erase this. Okay, so therefore, don't complain too much that why you're not writing that Lagrangian to me. It's been almost 3 weeks. I don't see the Lagrangian yet. Because All right, so okay, let's reverse this argument again. Then here is what I'm gonna do. So this is a quadratic equation on some operator, but let's take the following steps. Now I'm gonna view this as a quadratic differential equation on some function first. Okay, we will have a much more systematic development. For now, I'll just tell you the basic logic behind this. I'm gonna view this as a second order differential equation on the function rather than the operator first. Then you can solve this. So you're gonna solve this equation by taking an ansatz. So here's my ansatz. And guess what? In momentum space, I mean, that's exactly how it is engineered, right? So obviously, you can solve this equation in momentum space like that. What it means is that now, as a function rather than an operator, I can solve this if I say that this thing always satisfies this condition, which means that this thing always has a feature that implements p squared is equal to m squared condition automatically. So therefore, now we're gonna get a solution of this form, which is now this. Still, I haven't fixed what A had to be, or what condition A had to satisfy yet. Okay, now I'm going to rewrite this in a way that by inserting 1. Okay? The one that looks a bit fancy, so I'm going to insert data function and then minus. Alright, that's 1. This is Heaviside step function, which is one that way, half of that. This one is 1 half the other way, so it's the sum of the two, it's 1. Okay? So let's split it into 2. So the first piece, I'm going to be careful. So I have that delta, and theta, exponential. And then I have A over P over 2 pi. So that's the first piece. Yes? So I just finished writing the first piece. And then I have a second piece. So here, let me write it down.
There is a version.
I'm sorry?
There is a version of one piece.
Say it again. Yes.
Iteration along is P2.
Yes. No. Sorry about that. I actually meant the following. 2 pi to the 3, right? So I just have 2 pi. Okay, in case you see what I'm doing. So hopefully you recognize that this, right, is Lorentz invariant measure we talked about. Okay? And then the second piece from theta minus p. Okay, so for this one, you can do p sent to minus p. Let's see. So if you do the change of variable, then this becomes theta of plus p0. That's good. Instead, exponentially pick up the plus sign here. That doesn't change. So you're going to get the following expression. So if we repeat, let me already use Lorentz invariant measure. And then you're going to get it to the plus ip dot x, and then a of minus p over 2. Right? Okay, so then if we impose a reality condition on that, I mean reality, because we are dealing with a function. So then you can show that from this ansatz, in terms of that, you should be able to show that this means a of minus p is equal to a of the star p. Okay? Basically, under the reality complex conjugation, this flips this complex conjugated. And then you make a change of variable p to minus p, goes back to itself, and then this becomes a star of minus p, which should be equal to the original guy, and this is the condition. Okay, what we have learned so far. From this exercise, we'll learn the following. So by solving this Klein-Gordon equation, what is known as, so let me just write Klein-Gordon equation. in case you care about the name, here we go. To me, this is basically that equation, right? Then the solution, now just solution of a function, I get the following form. So then here's my solution. Okay, so this is a solution. Now, if I want to send this classical solution to quantum operator called quantization, once again, we will develop the machinery of quantization much more carefully. Here, I'm just going through very quickly. We, promote this to be an operator now, and then complex conjugate, so Hermitian conjugate operator, and that somehow appears to be a quantum operator that we have seen. Now, so therefore, morale was that, okay, I knew this, but then that P cannot be random, but it had to satisfy that. And what kind of condition should I impose on this field such that it satisfies that? But then I created leap. I just switched back to, okay, let's first interpret this as a function and first solve that. And then I want to construct a quantum field by taking a solution to that second order differential equation and promoting to the quantum operator. So far, it looks like you get a form that looks like a quantum operator that we constructed. But that's not the end of the story, because we have to check the causality. From this perspective, causality appears as follows. This is a second order differential equation, right? So you solved it, but when you solve the differential equation, you have to impose initial conditions. So let's take a Cauchy surface, or whatever the surface at fixed time. What are the conditions do I want to impose here as a boundary condition or initial condition for the second order differential equation in such a way that the choice of initial condition is compatible with the causality? Okay? So turns out that, one is obvious. So let's impose two boundary conditions as a second order differential equation. So this is equal time commutation relation. Equal time commutation relation. However, you should be able to read it that way, but at the same time, you should also be able to read this as literally this, that whenever these 2 points are space-like separated. Remember the argument, right? Whenever you have a space-like separated, you can use a Lorentz transformation to put it back onto the same time slots. The equal time commutation relation is just that condition. And then you want to impose the first boundary condition on field to satisfy that, which is compatible with the causality. Second condition, right? Usually if you have equation for something, you want to impose the first condition on this itself and second condition on the derivative of that. So the second condition, this is the first condition. Second condition is time derivative on one of them. Now it had to be this, which you can sort of derive by taking now the form and then plug in here, take a derivative. We would love to show this. Okay? Okay, so what have we done? What have we done? So here is a summary of now what I want you to say regarding this reversing argument point. So here, U story is that phi as an operator is my fundamental object. And then previously we had a okay, so let me reverse a little bit. So previously we talked about okay, phi should be linear in alpha of a dagger. Now we're gonna replace that with a condition that this has to solve Craig-Gordon equation. And one way to see that was if you solve this, it give you linear combination. That's one way of seeing it. Or in general, you could have said that y in this equation, it appears as that. In principle, you can have a some polynomial function of a phi. For instance, example like lambda phi cubed. In principle, such thing can appear. Okay? So linearity of a field in creation analysis operator is tied to the fact that I'm first talking about quantum field describing free propagation, not interactions. Because if you have interaction, one particle can turn into three particles. So one field, it seems like it is capable of producing three particles, right? Looks like you need to have a nonlinear composition of the creation analysis operators, which we are not doing. So basically, we have in mind that we're going to deal with what's known as a perturbation theory. That I don't have to worry about interaction for now, and then we will develop machinery how to deal with it once we understand the first part first. Okay? Okay, so then we say we're going to impose causality condition. Here, we traded that with the two initial conditions, right? With respect to this differential equation, which are these two. Okay, let me not just write it down. And then obviously we still have two Poincare invariants we talked about. What am I missing? Oh, we also use the permission. So that's the same thing. So basically now, in this language, we are speaking slightly different language, but this has been, reverted. Basically, I'm going to say field, I want to satisfy this with these two boundary conditions, compatible with the causality, and then Poincare invariance, and I might play with a real scalar field, but I also can play with the complex field if I want. Okay? So that's basically reversal of the rationale, how we can think about it. Okay. Yes, of course.
Even though we struck by different, I think we didn't say anything about the A and A. I mean, what is object? What is the? Well, I mean, alpha and alpha dagger mean.
In this construction, like for instance, why we have to interpret this as a correlation operator, why they have to satisfy, correct, so good. So that question can be answered by, so I said two initial conditions. So from the language of differential equation, you found a solution with unfixed coefficient. And you remember that when you solve differential equation, you fix the coefficient by now imposing boundary conditions. So therefore, if you impose these conditions, you will find out that alpha dagger has to satisfy the commutation relation that we already know from many-body Fox space. So this condition will be equivalent to say that alpha commutes with alpha dagger commutes with alpha dagger commutes in a way that we saw. This will determine the structure that this has to satisfy. And therefore, we learned that since alpha dagger satisfies the exact commutation relation of that of creation annihilation, I know that this thing does the job of creating annihilating particles.
Okay. The second condition can be come from first one.
This
or both are different.
Okay, so I will have another way of introducing this condition. Here I quickly said, probably you caught what I said. Take this and then this form and plug it in. Then you can derive this. So in a sense, you can interpret this as a compatible, consistent second initial condition with the first. However, there's a way to introduce and then motivate this condition independently, which is, let me just say that. So basically, next week or so, we will develop that machinery. So when we pass on from classical to the quantum mechanics, so we start out with what's known as a Poisson bracket, and then we promote it to the commutator with I, H bar. What about it? In the other way around? One. Oh. Nice. Very good. Somebody is listening. What happens to the rest now? So there's a Poisson bracket, and then you promote it to the commutator, right? Then, basically, that's the next discussion. There's a generalized coordinate and then a conjugate momentum. So here, this represents the generalized coordinate of a classical field theory rather than classical mechanics. And then this is related to a conjugate momentum. And then I'm imposing I H bar, basically. But this has infinite number of degree of freedom, so I have to know how to say this is the same. So for instance, if you had A, B, here is an AB, delta. But you have X, Y as a labeling, so I need a delta function. This is literally that complete relation. But then what I said quickly was that this condition, which you wanted to say that, turns out to be completely compatible with the causality.
Professor.
Yes.
But that kind of derivation really depends on the formalism, canonical formula.
This.
Yeah, that's true. The reduction. Yeah.
You mean this?
Yeah.
Are you saying that it depends on which quantization scheme you use? Is that what you're saying? Sure.
But at first you said that such two boundary conditions are only imposed to make the theory concrete, right?
And especially causality.
Yeah. But that kind of explanation depends on the canonical formalism.
Yeah, this is the canonical quantization.
So it is what's strong, right? 이게 훨씬 더 강력한.
I understood that way too. But I'm just trying to understand in what sense you think. Are you saying this is much more strong or this is more? I guess you probably would say that this, I'm introducing this as a pretty general scheme or pretty general way to construct things. And probably you were saying that this is, for a very particular way of quantizing. Is that what you have in mind? I agree. Should I? Do you think I do?
I think you must have.
At least, once again, the way I view this, okay, in a sense, the way I not just me, I'm following good resources, but I put my own exercise part here and there. But the way I view the story is that we started out with the minimal assumption first, right? I just want to have a sensible quantum description, right? And then I constructed a quantum field. And then I wanted to reverse the argument such that, I don't have to remember all this exercise. I just need to remember a minimal set of conditions. And then this canonical quantization condition, which we require the notion of a classical quantum field theory and the quantization. That's, we talked about Lagrangian. And the way I introduced why we start out with Lagrangian canonical quantization is yet another, sort of bookkeeping machinery. Mnemonics, basically. So in that sense, I'm not sure if this is like separate story. This is yet another uplifted fancy toy that remembers all those sacred principles that have to be satisfied.
모르겠는데, 그러니까 저러면 해밀토니안 포멀리즘 반드시 도입해야 되는 거잖아요, 캐논이.
No, well, this is one way to get to that. You might say, in the path integral formulation, do you get to see this commutator of a phi and phi dagger? Principally, you can, but at the level of a correlation function, not just as an operator equation. Any objective computed path integral is time order correlation function, right?
저도 얼마 전까지 그렇게 알고 있었는데 저걸 유도하시다가 최근에 나한테
It is possible. I think one of the exercises to find the need to show why path integral is compatible with this was that exercise. Yeah. But anyway.
그러니까 제가 말하는 거는 저 바운드 컨디션 두 개를 주는 것은 그 라그랑지안이나 해밀토니안의 어떤 초이스 없이도
Yes.
그냥 띠오리를 커자리티를 가지게 하려면 저렇게 준다고 말을 하는 건 굉장히 재밌더라고요.
Yes.
네, 저 두 번째 바운드 컨디션을 설명할 때 저 캐논이 포멀리즘을 쓰는 것은 특정 포멀리즘을 찾고 이제 두 번째 거를 우리가 걸었다고 본 건데.
Well, again, I guess, I'm not necessarily objecting your point of view, but another related point of view that I wanted to say was that I view canonical formulation, canonical quantization, which is literally the next discussion, is a way of yet another, formalism, introduction of formalism, that if you follow the rules of that formalism, known as canonical quantization, will automate all these terms. So you speed up this result in a consistent way. I'm just viewing that way. You may take another formulation that also speeds up the same result. So I'm not sure whether it is fair to say that one is more restrictive than the other. I just have a machinery that spits out the outputs which are compatible with all these results. Okay. Okay. Any other question? Yes.
혹시 그럼 커절리티에서 인풋 했더니까 저 식이 나오는데 그러면 커절리티에서 불합성성을 왜 하나고?
I think that's somewhat separate. So a certain principle is applicable to any quantum system, not necessarily a relativistic system. It should be compatible, but it is more about if you have a two conjugate variable or conjugate object, you know, they have to satisfy certain relations. I mean, this is encapsulating Heisenberg on certain principle. Because Heisenberg on certain principle, if you remember the derivation, this is bounded by that kind of object. I forget the exact expression. So, okay.
근데 릴레이티비스틱 퀀텀 메카닉이라는 게 결국에는 논-릴레이티비스틱 합쳐가지고 지금 통합한 이론을 그러면 모든 양자 시스템에 대해
It is. Every quantum system has to satisfy this problem. And here is one way to see that. Good that you mentioned that, because I realized. You may remember our discussion when we first talk about, how to formulate the causality condition. We say, okay, if I have a reason 1 and then reason 2, which are, space-like separated, and then operator had to commute, right, with itself, right? And you might say, that's why we never worried about that in the non-relativistic quantum mechanics. Right? Sounds like you have to worry about it. As you said, it looks like this type of condition has to be satisfied every physics we see. But then why in the non-relativistic quantum mechanics we never ever even talk about that at all, right? It may be a relaxed condition, but it should be that such condition should exist there. I think one way to think about it is that taking a non-relativistic limit, this is basically V equal to C line, right? And then this one too. Basically, non-relativistic limit can be taken by setting C to infinity. But then we'll just collapse this to like that. So basically, it's closing up the discussion, the sensitive discussion. And then in non-relativistic quantum mechanics, you're necessarily here and there. Necessarily. Okay? So that's why probably there's no notion or instance where you start worrying about that kind of question. So therefore, that's why you only talk about time evolution. From here to there, they are manifestly causally related. Okay. Thank you. Well, I think it's not probably the best idea to start a new discussion. So here, let me just clarify one thing about the history. Then I'll start today. Well, it's not a clarifying history actually. It's just to clarify concept. So, probably I said that when we start seeing object like this. Yes, I said probably that this is positive energy or frequency mode, and this is negative energy or frequency mode. Did I say that? Did I? Okay. And then that motivates to write this as a phi plus and this as a phi minus. Right? And probably you might have also seen or heard that statement like an antiparticle is like propagating forward in time with negative energy, one bad thing, or positive energy but propagating negative time, something like this. Have you seen that? But also, in case you have appreciated in my discussion, I never ever talked about that kind of thing, right? I just said there's one particle propagating, another guy propagated two, just cancel each other. In positive sense and forward in time sense. So where they come from? So first of all, y minus IPX, coined the name of positive p, better statement somehow. And that's probably because, if you have evolution of a state, not the operator, okay? Evolution of the state, that goes like minus IHT, okay? From Schrödinger equation, right? Good. Now, so therefore, probably that's why. In that sense, historically, I think, I could be wrong. I'm happy to be wrong. Historically, when people first studied the relativistic quantum mechanics, not the quantum field theory, and they wanted to study quantum mechanics of a relativistic scalar particle, and there's a Klein-Gordon theory. And if you find a solution to the wave function, not the quantum field, you might get this decomposition. Exactly the way I did today, right? I just solved the equation, the second order differential equation, as a function rather than an operator. Then obviously, to genuinely correctly interpret this as a positive energy, this is negative energy, please. Right? As a state. I stressed that several times. But how about in terms of, in a sense, of a quantum operator? And versus, you may remember seeing like, if I have a quantum operator now, acting on this, I told you that this has e to the plus I p dot x. I never complained about that, right? And you might say, oh, is this that? That looks like everything is negative energy. Is this consistent? So here's one way to see that. So when we match between Schrödinger picture and Heisenberg picture, right? So psi goes like a u psi, but then operator, if you again remember this discussion, if you switch that psi dagger O, now I just interpret this is how operator transform, right? So what it means is that the quantum operator had to transform as minus IHT. I'm just looking at only time translation. And then you saw that this is actually, so let me just look at the delta t instead, okay? T minus delta t and x. Do you remember that discussion? Good, so that's how I do it. So then we can actually check it, whether this plus sign is consistent with the correct time evolution of the quantum state. So suppose I imagine it producing a particle at time t. So this thing include I, E, t. Okay? So I produce a particle at t. But let's do the same experiment. But I'm going to produce a particle at time delta t later. Then correct thing to do is now use operator with a t minus delta t. Well, let me just be sloppy. X minus delta x acting on the back, according to this transformation. Correct? And then this will give me e to the ip dot x minus delta t. Sorry, x. In particular, this will include e to the minus I, zeroth component, e delta t, and then original wave function. Yes? So indeed, compared to this, it evolved according to correct state transformation. Okay, it just, state versus operator, if you just be a little bit careful, it is all consistent. And at the level of quantum operator field, I will not call this positive, negative thing. Okay, it's just a naming scheme, nothing more than that. All right, so probably that's enough for today. And next week we will start canonical computation. Thanks.